Hey everybody, and welcome back. First of all, I'd like to apologize for the quality of this diagram. I could not find a better one for exactly what we needed. In any case, today we're going to be talking about the structure of nerve cells, the role of ion channels in nerve cells. I'm sure that many of you have heard about potassium channel openers as a potential treatment for tinnitus. We're also going to be talking about action potentials and spike timing dependent plasticity, or Hebbian theory. And we're also going to be talking about why Neuromod Lenire, based on the principles that we will be discussing today, does not work. Now, I'll try to keep it as simple as possible, but if you guys truly care about understanding these conditions, then this video is absolutely crucial. Now, here is what a typical neuron looks like. There's many different types of nerve cells or neurons in the body, and as you all may know from school, neurons are specialized cells that communicate with each other through electrical and chemical signals, allowing our brain and body to function. Now, there are many different types of neurons in the body, but the main ones that we're going to be discussing are something called interneurons, because these are the neurons that are responsible for communication between sensory neurons, like for touch, and motor neurons, like for movement. Fusiform cells, the cells that are responsible or have a very significant role in tinnitus generation, are interneurons. They pass these signals from the cochlea further up the auditory pathway. And these neurons, these fusiform cells, by Susan Shore's theory, are the ones that become synchronized or hyperactive. Now, fusiform cells, the cells that are responsible for tinnitus generation, the ones that become synchronized, they look a little bit different than the ones we have up on the screen, but generally speaking, the core structure is the same. If anybody is curious, fusiform cells take more of a cone shape, and they have the dendrites extending in all directions. A little bit more on that later. Getting back to the default structure of nerve cells, let's start by taking a look at the diagram here and me explaining to you what all of this is. Let's start with the cell body. This is the cell body. It's also called a soma, which in Latin means body. And from the soma, we can see these little tendrils extending. Now, these are called dendrites, and they are absolutely crucial in the communication between neurons. We also have something called the axon. As you can see on the diagram, it's a little bit confusing, but the axon is this long, extended part of the neuron down which the nerve signal goes to the axon terminals. Now, the axon terminals are these little tendrils at the end of the neuron, and the axon terminal sends the signals to the dendrites of the other nerve cell. Now, as you can see in the diagram, the presynaptic neuron is the neuron that is before the synapse, and the postsynaptic neuron is the neuron that comes after the synapse. Now, these terms are very important today, so I recommend that you think a little bit about it and that you remember it. Now we're going to get into stuff that's a little bit more complex, but bear with me, I'm going to try to keep it as simple as possible. So how do neurons actually transmit signals? This is where ion channels come in. Ion channels are like gates that are embedded in the neuron's membrane or the skin that allow specific ions or charged particles, as you guys can see here, to flow in and to flow out are sodium, potassium, calcium, and chloride. As you can see, all of them are charged differently. You can imagine the nerve cell or the neuron to be like a battery that can become either more positive, the more ions, the more positive ions you have, or become more negative when the positive ions flow out or when the negative ions flow in to kind of balance it out. Now, the first type of ion channel that we're going to talk about are voltage-gated ion channels. These channels are distributed throughout the neuron, including the axon, the soma, or the cell body, and the dendrites as well, but their density is different. The largest concentration of voltage-gated ion channels is at something called the axon hillock, which is the beginning, so to speak, of the axon. Now, what do these ion channels actually do? The reason why they're called voltage-gated ion channels is that they are activated by changes in the electrical membrane potential. Now, the electrical membrane potential is what I mentioned before. It's like the changes in positive and negative charge, to put it simply. Now, the reason why voltage-gated ion channels exist is to support the signal throughout the cell, all the way down to the axon terminal. Now, obviously, as we all know in electricity, electricity can potentially be lost as it flows on. So to make sure that the signal is just as strong, or generally as strong as it was when it first entered the cell, the voltage-gated ion channels make sure throughout the cell that the signal is supported and correct and does not lose the charge as it moves on through the axon down to the axon terminal and eventually to the next neuron. Now, the next type of ion channel that we're going to talk about are ligand-gated ion channels. They are typically located on the dendrites and the soma as well, and they are absolutely crucial for synaptic transmission or communication between the nerve cells. Now let's take a closer look at the synapse. As you can see, I've kind of zoomed it in here. Now, to understand what we're going to be talking about, I'm going to explain some of the terminology. Now, the synaptic cleft is kind of this empty space between the axon terminal of the presynaptic neuron and the dendrite of the postsynaptic neuron. So you can imagine this part right here being this axon terminal right here, and this part right here being the dendrite that is right here. Now, what is actually going on here? When the nerve impulse reaches the axon terminal, what it does is that it causes the calcium ion channels to open. The calcium ions rush in to the axon terminal, and they trigger the synaptic vesicles to release something called neurotransmitters into the synaptic cleft. Now, what are neurotransmitters? I'm not going to go too much in detail here, but the main neurotransmitter that we're going to be talking about is glutamate. Now, excitatory neurotransmitters excite the neuron and cause it to fire off the message. Now, besides glutamate, there is also epinephrine and norepinephrine, but we're not going to be talking about those today. And there are also something called inhibitory neurotransmitters. They block or prevent the chemical message from being passed any further, or they can just dampen the signal. Now, if we talk a little bit about the process, once the nerve impulse reaches the presynaptic terminal, the amount or the strength of the nerve impulse is kind of transferred by the neurotransmitters. So the neurotransmitters themselves contain the information on how strong the nerve impulse is. It passes it to the ion channels on the postsynaptic neuron, to be more precise, the ligand-gated ion channels. Now, the ion channels that receive the signal from these neurotransmitters, well, it's really complex, but basically there are something called AMPA receptors. Now, these AMPA receptors receive this neurotransmitter, or the excitatory one, that is glutamate. And depending on the strength of the nerve impulse that is transferred by the neurotransmitters, these ion channels will open to a certain degree, and they will allow the sodium ions to rush into the postsynaptic neuron. Now, what happens when the sodium rushes in through the ligand-gated ion channels is that it causes the charge of the postsynaptic neuron to increase to a certain level. Now, after this certain threshold is reached by the sodium ions rushing in through the AMPA receptors, or the ion channels, it causes the nerve cell to reach a certain threshold. The positive charge of the postsynaptic neuron to spike really intensely, which is called an action potential. And we're going to talk about action potentials here in a minute. Now, more specifically, the action potential is the electrical impulse that travels along the axon through the synapse and to the postsynaptic neuron. Now, why are action potentials so important? Action potentials, as I've mentioned before, are the communication mechanism between neurons. And when a person has tinnitus, his fusiform cells are hyperactive, and what that means is that their synaptic connections are stronger than they should be. Ergo, too many action potentials are being fired. Now, usually, when a person hears something, the nerve impulse travels through the auditory pathway from the cochlea, or the ear, the little snail thing I mentioned before in my previous videos, and it travels down through the auditory system to the dorsal cochlear nucleus. Now, the nerve cells, the fusiform cells that are hyperactive in the dorsal cochlear nucleus, they are firing too many action potentials. What that means is that this threshold is too easily reached. There's too much sodium influx happening when it's not supposed to be. And when one action potential is fired, it travels to the next neuron, and then another one is fired, and it travels to the next neuron, and it happens over and over again. What is actually supposed to be happening in healthy people are these failed initiations. The initiation has to fail for the person to not hear anything. Yes, or for the neuron to be in the resting state. But unfortunately, with tinnitus, the action potentials are being fired, even though they're not supposed to be fired. Now let's talk about spike timing dependent plasticity, long-term potentiation, and long-term depression. What STDP is, it's a form of synaptic plasticity, where the strength of a connection between neurons depends on the timing of their activity. Now, the history of STDP is very, very immense. I'm not going to be going into it. But what you need to know is was studied by Donald Hebb, or it's also called Hebbian theory. The two phrases that are absolutely super duper important in spike timing dependent plasticity are neurons that fire together, wire together, and neurons that fire out of sync, lose their link. Now, more in detail on that. When the presynaptic neuron fires just before the postsynaptic neuron, or when the action potential fires right before the action potential of the postsynaptic neuron, this timing triggers a process known as long-term potentiation. It strengthens the connection between the two neurons. However, if the postsynaptic neuron fires out of sync or right before the presynaptic neuron, it leads to long-term depression or the weakening of these signals. Now, the explanation as to why the nerve cells work like this is very massive, and I might make a video on it in the future, but for now, we're going to be talking about the basics. LTP, or long-term potentiation, which is the strengthening of the synapses or the synaptic connections, is much easier to achieve than long-term depression. It only requires rapid and repeated firing of action potentials from the presynaptic neuron. This is like the normal process. Yes, this creates, or it causes, a strong influx of calcium, like we discussed previously. Now, the cell feels these strong influxes of calcium, or the timing of these influxes of calcium, and this triggers kineses that increase AMPA receptors. It increases the amount of receptors that receive the sodium from the presynaptic neuron, and it makes these synapses more sensitive. Now, the tendency for LTP to occur more easily is actually one reason why tinnitus often worsens over time. Hyperactive neurons in the auditory pathway can repeatedly reinforce their own activity, especially if they're not counterbalanced by LTD. Each time they fire in response to a sound, they strengthen their connection, making the tinnitus louder and more persistent. On the other hand, long-term depression, or LTD, requires much more specific conditions to happen. It involves a very specific, low-sustained calcium influx instead of the rapid spam of the action potentials, aka the calcium influxes for LTP. This lower calcium level, or this very specific level of calcium that is felt by the neuron after the postsynaptic neuron fires at a specific time before the presynaptic neuron, the body feels it as a message that the connection between these neurons is not as important. And this lower calcium level activates phosphates, which remove the AMPA receptors that receive the sodium for the initial threshold. Now, because LTD is pretty hard to achieve, I mean, we very rarely are in a resting state, the brain doesn't as easily weaken hyperactive connections. This is part of the reason why tinnitus often persists or worsens. It's much easier for the brain to reinforce the pathways that are active than to scale them down. For example, Susan Shore's device kind of hacks the neurons into having the postsynaptic neuron fire first, or fire before, the presynaptic neuron. Now, in our day-to-day lives, very rarely do we have total silence. And people who do actually avoid loud noise, they avoid going to concerts, or they stay in relative silence, especially for the more severe group of tinnitus sufferers. This leads to less action potentials being fired, and this subsequently leads the body to feel this lower calcium level, or this lower calcium influx that happens, which eventually does lead to long-term depression. But this requires months and months of silence, which, many very catastrophic sufferers do have. And that's exactly what happened to me. My tinnitus and hyperacusis only started improving after I removed all external irritants. For example, I also treated my somatosensory issues like my jaw and my cervical issues. And removing these irritants, removing the noise, removing just all of these potentials, all of these potential action potentials, as I guess you could say, led to a lower calcium level, which my body interpreted as these connections not being so important anymore, and removing the AMPA receptors, not allowing for the threshold to be reached. So the reason why my tinnitus got better with time basically was lack of input, increased resting state of the neurons, which eventually led to the removal of the AMPA receptors. And now, instead of the action potential being fired, I have the failed initiations. Now, I'm sounding kind of redundant here, but the goal of the Susan Shore device is to use these very precise timings to try and achieve the failed initiations. Artificially, I guess you could say. Now, before I move on to talking about Susan Shore's device and Lenire, let's talk a little bit about Gaba. Now, Gaba, as I mentioned before, is an inhibitory neurotransmitter. What that means is that it binds to these specific chloride. Now, a little bit of a commentary here. If you guys are wondering how the heck is a presynaptic neuron supposed to understand if the postsynaptic neuron fires first? Well, in neuroscience, there is a term called retrograde signaling, or retrograde neurotransmission, and it refers more specifically to the process in which a messenger, or a retrograde messenger, such as anandamide or nitric oxide, I guess, is released by the postsynaptic dendrite and travels backwards to bind to the axon terminal of the presynaptic neuron. So that's how the postsynaptic neuron and presynaptic neuron communicate with each other. Now, more about Lenire. Lenire as a device plays a continuous preset of noise, and I mean this noise never stops. And it also shocks the tongue at the same time. Now, why is this ineffective for inducing LTD, which we need? Well, if the noise is being played continuously, that means that action potentials are constantly firing. And when the action potentials are constantly firing while listening to the noise, then how is the somatosensory system supposed to receive the adequate stimulation at the correct timings? That's the first thing. The body cannot understand which one of these signals is presynaptic or a postsynaptic spike. The next thing is that the fusiform cells that are hyperactive are grouped together to certain frequencies. So there are certain pathways of fusiform cells in the dorsal cochlear nucleus that are, I guess you could say, fine-tuned to specific frequencies. And the fusiform cells that are hyperactive, or the tone, the tinnitus tone that we hear, for example, the high frequency screech or whatever, these fusiform cells need to be targeted. The specific fusiform cells that are hyperactive of a certain frequency need to be targeted in order to be stimulated correctly. Lenire plays white noise or just other presets that just target like all the fusiform cells, or just, it does not precisely target the fusiform cells that are hyperactive. That's another problem. And this increase, or this influx of noise energy that is entering the cochlea and through the dorsal cochlear nucleus, this can actually induce long-term potentiation because of how much of it there is. So if a person who is particularly sensitive is using the Lenire device, they can actually worsen themselves over time. Not to mention the tongue stimulation, ergo the hypoglossal nerve, the 12th cranial nerve, is less prevalent in the dorsal cochlear nuclei. It's weaker. I don't know why they chose the hypoglossal nerve as the somatosensory stimulation, because the trigeminal nerve or the upper cervical nerves are much more prevalent in the dorsal cochlear nuclei than the hypoglossal nerve. So the decision to choose the tongue is also weird. I don't know why they chose it, when the other cranial nerves that I've mentioned, like the trigeminal and upper cervical, provide much stronger somatosensory connections in the dorsal cochlear nucleus. Now for the Susan Shore device and why it actually does decrease tinnitus objectively, why it actually decreases these synaptic connections as compared to Lenire. First of all, the somatosensory stimulation targets the trigeminal nerve or the trigeminal ganglion or the upper cervical nerves, which are very, very prevalent in the dorsal cochlear nucleus. The somatosensory connections to the fusiform cells, more specifically the hyperactive fusiform cells, are much stronger, and that allows for a more prevalent stimulation to happen. That's the first thing. And the second thing, the Susan Shore device does not play continuous noise. It plays bursts of millisecond noise. And what these bursts of millisecond noise do is that they prime the hyperactive fusiform cells. By the way, these bursts of noise are targeted specifically to the user's tinnitus frequency. They're not random, and they are very precisely set up to provide the action potentials required for long-term depression without providing too much sound energy to potentially induce LTP. So basically, the Susan Shore device, it primes the hyperactive fusiform cells, and when these fusiform cells are primed, their synaptic connections to the somatosensory system are also primed, so they're ready to go. And when the somatosensory stimulus happens, it provides the adequately timed postsynaptic action potentials that the body or the nerve cells then feel to start inducing the AMPA receptor removal process. And as we know, when enough AMPA receptors are removed, there cannot be an adequate sodium influx for the action potential to start. Hence, the synaptic connections become weaker. And the cell cannot fire an action potential, or those failed initiations that I showed you on the graph. And consequently, the tinnitus becomes objectively quieter. That's all that I wanted to explain to you today. Hopefully you enjoyed my scientific explanation as to why Lenire does not work and why Susan Shore's device does work. If you have any more questions about my trials or about the Susan Shore device or about basically anything, you can join my Discord server. You can find me in the list of names. I am the owner of the server, and my name there is Anthony, or at Tony the Catman. Yeah, I know it's a pretty cringe username. And you can send me a personal message, or you can tag me in the server itself and ask away. The server does have many intellectual individuals, so I'm not the only person who can help you out with your tinnitus case. So if I happen to not be online, you can definitely either refer to my administrators or send a message into the appropriate channel and receive a response. By the way, real quick, something I forgot to mention in the middle of the video is the prevalence of mechanical issues in potentially causing and worsening tinnitus. I'm going to make a video on this in the future, but basically somatosensory connections can also, if they are stronger, like for example with neuroinflammation or with hurting your neck or just having jaw issues, if there are too many somatosensory or too strong somatosensory action potentials, this can actually prime the fusiform cells to becoming more hyperactive. And that's exactly why people with more mechanical issues like cervical issues or TMJ, temporomandibular joint dysfunction, can actually have worse tinnitus because the fusiform cells are more easily primed for action potentials. That's all for today, and I'll see you later.